Okay, in this video we will explain one of the cases that we have when we are solving a linear system. Remember that a linear system, it goes like, it looks like this. Cx plus dy. And then usually the procedure for when you are solving a linear system is you consider the matrix A, B, C, D, and then the characteristic polynomial, which is lambda squared minus the trace of A lambda plus determinant of A. This is the characteristic equation. And we're going to consider the case when lambda 1 and 2 are of this form. Alpha plus or minus beta I with beta bigger than 0. Then maybe before I do that, let me remind you that when you have like a function like e to the 2t plus, say, let's say 3 sine of t times I, right? Then for every t we have a complex number, but then the real part of this, what I call the real part, would be the e to the 2t, the part that doesn't have the I, and the imaginary part would be the 3 sine of t. Remember, the imaginary part doesn't have the I, is the what is next to the I without the I. And that works also for vectors. Let's suppose that you have this vector like this, like sine of 3t plus cosine of t minus 3i, let's say e to the 21t. Then if you have this vector, then the real part of that vector would be a vector as well. It would be e to the 2t, and here sine of 3t plus cosine of t. And the imaginary part of this vector would be 3 sine of t, and here would be 3 e to the 21t. Right? This is the imaginary part and the real part of a vector and a real number. Okay, then what do we do? Once we realize that we are in this case, we need to consider this eigenvector, this eigenvalue, sorry, lambda equal alpha plus beta I, with beta positive. You just pick one. And then we compute the eigenvector. In order to compute the eigenvector, we do the system A minus parentheses alpha plus beta I, close parentheses, times x plus by equals 0. And here you have cx plus d minus parentheses alpha plus beta I times y equals 0. And then you need to pick an eigenvector for this. Notice that a possible choice would be like, you can make x equal negative b. You can pick x equal negative b. And you can pick y equal to this number. Notice that this number is going to be a minus alpha, right? A minus alpha, this minus goes here, minus beta I. This is a possible choice for your eigenvector. The bad news is that you have to deal with complex numbers. The good news, when we compare with the other case in which there were two different real eigenvalues, is that you don't have to compute a second eigenvector. You just need one. And then what do we do with this number? Essentially, what we do, let's call this the vector b1 and b2. Then what we do, we have to do some algebra. We need to compute the real part and the imaginary part of this vector, of the vector e to the alpha t times cosine of beta t plus I sine of beta t times this vector b1, which is negative b, and b2. Remember, we can compute the real part and the imaginary part. And then the general solution is going to be just x and y equal to C1, this real part, plus C2, then this imaginary part. Remember, we need to expand this, find out what is the real part and the imaginary part. This is the part that is a little tedious, it's long and boring, but that you have to do. And then when you expand this, you can see this is the real part and the imaginary part. And then you have a vector here, another vector here, and your solution is just that. It's x, y, and you can say x is the first part and y is the second part. Let's do a particular example to see how it works. Let's suppose that we want to solve, let me leave that part and see how much we can cover. Let's say we want to solve this system dx dt equals 2x plus 2y, and then dy dt equal negative 2x plus 2y. And let's suppose that we want to have some initial conditions. No, let's suppose that we want to find the general solution for this. Then we compute the matrix of the system, which is 2, 2, negative 2, and 2. And then we compute the trace. Trace of A is 4. And the determinant of A is 2 times 2 is 4. It would be 8. And then we have to solve this system. Lambda squared minus 4 lambda plus 8 equals 0. Here factoring is not going to work. You have to either complete the square or use the quadratic formula, and you will see that your values for lambda, the solution of this, is going to be 2 plus or minus 2i. That's the value for lambda, and that means that when you think of this as alpha plus or minus beta I, then you realize that your alpha is 2 and your beta is also 2. Then we need to compute an eigenvector. Let's compute the eigenvector for this. Then we say the eigenvector for lambda equal 2 plus 2i. Then we solve this system. We do 2 minus, here you have to be very careful with your parentheses, minus lambda. But since lambda has two parts, it's important to write a parenthesis here, 2 plus 2i, and then you close the parenthesis, and then times x plus 2y equals 0, and here is negative 2x plus 2 minus lambda, but lambda is 2 plus 2i times y equals 0. Then this is equal to what we have here, minus 2i, 2 minus 2 is 0, minus 2ix plus 2y equals 0, and negative 2x minus 2iy equals 0. We can pick as a solution, we can pick x equal 2 and y equal the opposite of this, 2i, or we can just pick pick any multiple, let's say 1 and I. You pick that, and that's your eigenvector. Then here it comes the algebra part. The algebra part is we need to compute this expression, which is e to the 2t times cosine of 2t plus I sine of 2t times v1, v2. In this case, v1 is 1 and v2 is I. Notice that we are multiplying a number by a vector. How to multiply a number by a vector? We multiply the number by this entry and then this number by this entry here. Then when we do that, we get e to the 2t cosine of 2t plus e to the 2t sine of 2t times I, right? When I multiply this by this. Now, when I multiply this by this, I'm going to write first, notice that I times I is -1. Then I'm going to do this term here first. It's negative e to the 2t sine of 2t. And then when you multiply this, plus e to the 2t cosine of 2t I. What is the real part and the imaginary part? The real part of that expression there is an e to the 2t times cosine of 2t, and the negative e to the 2t sine of 2t. This is the real part. And what is the imaginary part? The imaginary part is the part that has the I. It's an e to the 2t. Let me erase this part here. And don't forget, I will be using this very soon, right? The real part is this part times C1, and this part is the imaginary part, but I will erase it now. And right now, I'm doing this part, the e to the alpha t times cosine of beta t. I'm going to erase it. I already compute the eigenvalues. And then let's provide the answer. This is e to the 2t sine of 2t. This is the part that is multiplying the I, and e to the 2t cosine of 2t. Then this is the real part and the imaginary part, and therefore our general solution is xy times c1, the real part, which is, let me factor the e to the 2t. This is, you can always do this, e to the 2t times cosine of 2t negative sine of 2t plus c2 e to the 2t, the imaginary part. I'm factoring the e to the 2t, then I am left with sine of 2t and then cosine of 2t. Then the solution is going to be, if you want to write a separate, x equal, I can factor an e to the 2t, write it better, e to the 2t times c1 cosine of 2t plus c2 sine of 2t, and the y is e to the 2t, and here we have negative c1 sine of 2t plus c2 cosine of 2t. This would be the general solution. As I mentioned before, the general solution is supposed to have a c1 and c2. I think I will stop here.